welcome to the course on FPGA based signal processing systems. Finite impulse response filters, we are looking at it, and then the FIR filter, which the types what we had learned in the previous lecture, type 1, 2, 3, 4, symmetric and the antisymmetric cases. For example, we take if n is 5, in that case the symmetric about n equal to 2. So h of n is symmetric about 2, that is 3, we can have 4, and then this side 0 and 1. So if that is the for n minus 1 coefficients here, type 1 filter impulse response, how it would be and what is the response we would get it. So the coefficients, the restricting that n here to, that is n minus 1, which is 4, the impulse input can be represented L of n minus 1, n minus 2, n minus 4. This h0, h1, h2 are the coefficients of the filter, depends on the h0, h1, h2, h3, h4, that output would be h of y of n or h of z here. H of z represents the response. So frequency response, we get that replacing this z here with that e power minus j omega. So that e power minus j omega, the z with e power j omega, and then z power minus 1, so it is become e power minus j omega, h of 2 e power minus j 2 omega, similarly h of 3 e power minus j 3 omega, h of 4 e power minus j 4 omega. So the coefficients 1, 2, 3, 4, 5, these 5 coefficients they have, and this we have considered symmetric about h2. That means the h1 and h3, that is would be same, and h0 and h4 would be same. So taking this e power minus 2 omega, that is common to this equation, that is here h0, so you have this minus 2 omega, so you get the plus j2 omega here, and here plus j omega in this component, and here this is h of 2 simply, and h of 3 is minus j omega and minus j2 omega. So now the coefficients we set about the h of n, which is symmetric about n equal to 2, that means h0 and h4, the first and the last coefficient would be same, and the next two, 1 which is around h of 2, 1 and 3 will be equal. So in that case, h of e power j omega, that is frequency response, equal to this equation. Now we have replaced this h of 3 with h of 1 and h of 4 with h of 0. Okay. So then simplify this, you get e power minus j 2 omega is this is h0 and h0 here. So e power j theta, e power minus j theta, so which results in cos 2 omega, here theta is 2 omega, and divided by 2 results in this 2 here to replace, and these are the two things h of 0 results in. Similarly, h of 1 gives the 2 h of 1 into cos omega plus the center terms and coefficient h of 2. So when we have this type of characteristics, that we solve the amplitude response, when we take that in this, we can have this results in the amplitude response, and this would result in the phase response. So if we take the amplitude of this magnitude, so we have h of e power j omega, in which 2 h of 0 cos 2 omega, 2 h1 cos omega plus h of 2. If we can take the magnitude as well in this case, so the phase response equal to the minus 2 omega, in the one which is having, we had in this equation, e power minus j 2 omega, this 2 omega minus 2 omega here as the phase response. So minus 2 omega, and here, so that would be for ha of e power j omega, the positive magnitudes are the frequencies, that would be minus 2 omega, and the negative side it is minus 2 omega minus pi. Okay, so when the frequency is negative and the positive thing, so you have the ha of omega, which is, this is amplitude, the amplitude response is greater than 0 or less than 0. So in that case, this is going to be minus 2 omega and minus 2 omega minus pi. So that can be obtained from this h of e power j omega, what is the phase response, and then what is the magnitude response as well. So this is for type 1 FIR filter, in which the coefficients which exhibits the linear phase characteristics, the phase would be linear. And then if we have this antisymmetric case in which about the center point, so that in the taking the type 3 one, okay, in which H2 is 0, the considered the center one is 0, and H0 is minus H of 4, and H1 is minus of H3. In the same coefficients what we have here, if we just replace them, this H of 0 and H of 1, so with these sign terms, so it would result in sine 2 omega, and H of 1 is sine omega 2 of 2 j e power minus j omega. So from this, that amplitude response, we get that this is contributing to the amplitude response, simply replacing in the previous example that the coefficients, that it would result in sine of omega. So the phase response is minus 2 omega plus pi by 2, and the amplitude, when the amplitude is greater than 0 and it is less than 0, it is going to be minus 2 omega minus pi by 2. So then this gives the response, and for the linear phase FIR filters. It's an example of type 1 and type 3. It can be extended to other types as well, depends on the filter coefficients, how it is symmetric or antisymmetric, in this case even or odd number of filter coefficients. So type 1, type 2, type 3, type 4 can be obtained in the design. So there are 4 types of FIR filters, depending on the coefficient symmetries G and the length here. So if we take the linear phase FIR, so the phase characteristic we had seen. So with this, what would be the structure of this linear phase FIR? This is in the type 1, we had this coefficients. So the generalized form of that, because if you have seen in the previous lecture, we had just taken x of n, and there is an h of 0 delayed for n taps whatever, and summed it up at each stage. But instead of here, we have the coefficient, two coefficients equal. So for example, H0 and H4 equal. So H0 is this, and if we get back here, this is going to be again H4. So we need not have the H0 delay and one more H1, H2, H3, H4, and then sum it up each stage. Instead of that, H4 and then H1 are brought here as a common term, that is H0. Okay, so this reduces this multiplication, which is having the only one multiplier here, that are storing this coefficient, one coefficient storage sufficient to have this. And similarly, the next coefficient H1, that is H1 and H3, this can be if it is symmetric about H2. Okay, so this would give the H2 1 here. So from n equal to 5 minus 1, that is 4 by 2, that is 2h of 2 here. So in the previous case, that is a type 1. So we can see the combined version of this structure. The coefficients are combined here. Okay, so this is the last the coefficient last to the least one, and here is the last coefficient or this last coefficient which comes as a center point of the FIR filter coefficients, as we have shown in the previous case. So this structure is again the linear phase FIR filter, wherein the coefficients in the first case, what we had, the coefficients are not of symmetricity, whereas here in the linear phase it is with the symmetricity, that whether it is symmetric, midpoint symmetric, or midpoint antisymmetric cases. So this gives the type 1 and type 2. Similarly, the one length of the filter would be more. So this is going to be the delay. You can see the delay which is coming over here. So if we have the odd length and even length, so type 2 is here, which is having x of n and the delays, and similarly h of 0 and h of 1 are summed up here the previous stage. So if we don't have this here, for example, n is 6 or to 4 by 2, it is going to be 2. So even length and odd length coefficients, the type 1 and type 2 structures are shown. So the difference would be only one delay which is extra over here. in the structure. So this structure uses the delays in the structure, and the number of coefficients are getting reduced in the linear phase FAR filter structure. So when we write a very long code, if these coefficients are same with symmetricity, then we can use this particular this structure. So for the design of this FAR filters, one of the methods for the FAR filter design is this windowing method. So to design the FAR filter using windows, then we need to know about this windowing concept. So what is the meaning of windowing here? So when we have a signal, if we want to if you are just the signal is truncated for a finite duration. So if the incoming signal which needs to be truncated for a particular duration, so and then zoom it or see that what is in that the truncated duration. So for that, these windows have been used. What is the meaning of if when you truncate that signal, whether you are sharply cutting off the signal, or you can use as tapering or smoothing windows in that amplitude can be smoothly brought to the zero on both the sides of the truncation. So the straight truncation, it creates serious problems in the spectral spreading and leakage. So it would, if you see the windows in which there will be leakage in the spectrum as well, in a spectrum in the if you have these truncated ones, yes, the leakage will be minimum, or this to solve this we can see this increase this window length, and tapering can be done. So smooth windows can be used for that purpose to reduce the spectral spreading. Also, we can see the reciprocal nature of the window length and the bandwidth. So if we take suppose a rectangular window in which the number of samples are shown here. This is the window, discrete window, it's WN rectangular, and which has this LW minus 1, it is n minus 1 what we had used in the previous examples. So 0 to n minus 1 samples in the window, that is filter coefficients. Anyway, this coefficient, this length is corresponding to the window, and number of samples is HW of n. So when that, in this case, when we take the Fourier transform of this Wn, which is W of e power j omega, so the rectangular function leads to this sinc function in the Fourier domain. That is you have the sinc function obtained from this, and the length or the width, and when we have this magnitude of this W of e power j omega, then all the sinc values here over in the sinc function, you get them as positive. Okay, so that's why you have all of them as positive. This is the magnitude. So actually the rectangular function which is giving the sinc function in the Fourier domain. So for frequency response of it is sinc function. So which has the bandwidth. This is the bandwidth which is 2 pi by L omega, where L omega is the length. Okay, so that is reciprocal of if you have more number of samples here, it would result in that band is less. The bandwidth would be here less. So it is, and if you have less number of samples, you have the more bandwidth. So it is having the inverse relationship with this, and this part, this figure shows the same response of the window frequency response with the 20 log scale. So which shows this is called the main lobe here for a window function. This is the main lobe, and these are side lobes of spectral leakages. Main lobe and side lobes needs to be understood for the design, because it plays an important role in the design of this. What is the characteristics of the filter? The main lobe and the side lobes. So if you see the first side lobe level, it is minus 13.3. So from 0 dB, this is minus 13.3, and then rest of the source. So this suppression from here to here. Okay, so this is fixed for the rectangular window. So this side lobe width is not, it is again matter, and main lobe width, in which this main lobe width can be controllable using the number of samples in the window function. So if it is more, and this main lobe width will be narrow, it will be less. So what is the meaning of this narrow window? That means you have this magnitude that frequency response is maximum here and it is 0 over at these points, and if the leakage is, it would also pass this. If it is a filter, then filter characteristics, it would also pass this. It's a window function anyway. We use this window and then design the filter. So with this rectangular window and its frequency response, so this is actually LW is 9 for that one. So what are the other characteristics can be observed in that? So the spectrum decays very slowly with respect to the frequency. Here the decay rate is very slow in the rectangular window frequency response. Also the side lobe is minus, that is first peak of the side lobe is 13.3 dB below the main lobe. This impulse response, if we consider this actually in a filter design, we have this ideal filter characteristics, that H of n, what is required. So it can have this spreads out its passband and produces unwanted ripple in the stop band, the windowing. So let's discuss this point in the during the design also, then how this is going to be affecting the design. And the case of window spectrum, narrow main lobe and small side lobes are desirable. In the narrow main lobe means what are the frequency, the maximum frequency which is to be done, and not have the main lobe to be wider, and the small side lobes are desirable. And so the ideal window is, if you take this ideal window, is a rectangular window of infinite length. So infinite length window cannot be used, so it needs to be truncated for the design. So how we are going to, this is a finite duration window, spectral width and side lobes are as small as possible. So finite duration window is required, and also the side lobe levels, which is actually the leakage, which is not the intended frequencies, so needs to be removed. So the desirable one, main lobe width narrow and side lobe widths are less side lobes, the ripples on the side lobes should be less side. And if we take some of the windows here, for example, this is a Hamming window which has the LW equal to 9 over in this blue lines. So it's a function again cos alpha windows. This is one type of cos alpha windows here, and the other one is LW equal to 10 Hamming window, which is just shown for this is with respect to the particular point here, and this is causal. It is not the negative sides are not shown. It is shifted to the positive side, H of W and the window function. So what is the window which has a desirable window, which is having the main lobe narrow and side lobe small, and for the given window type, this peak side lobe level, that is fixed in the for the rectangular windows at minus 13.3, and other windows also we can see them. So main lobe width shrinks as the window length increases. So we have seen this characteristics that in the if we increase the window samples in that, then the main lobe width would decrease. Also, window is based on side lobe characteristics and then adjust the window length to achieve the suitable main lobe. So which window, whether the smaller side lobe is required, which window to go for, and whether the main lobe width is suitable for the design or not, that then we need to adjust the number of samples in the window. So how we are going to use this will be I have given some of the characteristics which can be found also any of the text. Here is the window function, which is commonly used windows, and then how do we use them in the window design, that window method of FAR filters. So this window function for n is varying from 0 to that length minus 1 LW or n minus 1. Here the rectangular window in which the main lobe width is 4 pi by, we have seen 2 pi by LW both the sides, so 4 pi by that length LW n, that is 4 pi, and the roll-off rate is 20 dB. How it is the spectrum is decaying, dB per decade is minus 20 dB and dB per decade, and peak side lobe level is at minus 13.3. Whereas the case of triangular window, whose equation is given 1 minus 2 n minus 1 by n minus 1. So here this is a triangular or barlet window whose main lobe is 8 pi by LW. So if you change the tapering instead of straight truncation, the tapering is increasing the main lobe width to 8 pi. Okay, so this 4 pi here, this tapered window, it is the instead of rectangular, and the triangular is 8 pi. Whereas the roll off rate is minus 40. Yes, it's a side lobe, it is quickly decaying, and the peak side lobe level is minus 26.5. Yes, good reduction from the peak of the main lobe, so minus 26.5. And if we go to the Hanning window, the shape which I had shown in the cos alpha windows, which 0.5 minus 0.5 into cos of 2 pi n by n minus 1, and Hamming also, this thing 8 pi, these are giving 8 pi here, and minus 60 and minus 20. So increasing the main lobe width. So as we go on the tapering, it is increasing the main lobe width, and you can see the side lobe level is getting reduced, minus 13.3, then 26.5, and then go to 31.5 and 42.5, and it has a good roll off rate, but it is this is not how the side lobes are decreasing. Okay, so Hamming, and these are the common, some of the discrete time window functions. A few more here. If you go to the Blackman window, whose expression is given over here, cos 2 pi by n d n minus 1, and this main lobe width is 12 pi. So compared to the rectangular window, it is more, that is the wider main lobe, and then the roll off rate is good, yes, and the peak side lobe level is good 58.1 dB, which is the complete reduction in the side lobe, that the ripples are less and less. So and the Kaiser is another window which uses the Bessel function of the first kind and zeroth order one. So here we have the option of varying the window width. Also there are parameters which can help this alpha, which is a tunable window. Alpha can be fixed so that it varies with respect to alpha, the peak side lobe level. Also the main lobe width also varies, and 20 dB per decade side roll off rate. So these are common windows, and the equations are well known, and the peaks of this peak side lobe level is fixed for this windows which we have used. So these windows can be used in the design. So for example, here given, so the rectangular which is shown here in the blue line anyway, this is a rectangular window, and this one is a triangular window. Whereas if you take the rectangular window, you can see the magnitude, the sinc function, and the triangular window 1. So you can see the side lobe level decrease, this first side, or we can observe it in the log scale but better, and this is both of them magnitude of the sinc function over here. This is a sinc square function anyway, the red one. So here is we have the dB, and if we take the magnitude of this that response in log scale, so we have this rectangular window which is 13.3, and which this is far below that. You can see the ripple reduction in that, but the main lobe width, which is over here, and still this is increased in the main lobe width is increased without increasing any number of samples or anything. So here the characteristics of the window is that. So as we taper move on, the smoothening of the window, the truncation, then main lobe width increases and the side lobe width getting reduced. This is well known. So this is a function, and this is a spectra, and this is normalized spectra. So these are the different window shapes we can have. This is the one is the rectangular, this blue one, and then the green one is the Hanning, and the Bartlett triangular window, and Hamming over here, the black one, and there is a Blackman window here. So you can see the tapering used in this window compared to this straight truncation of the rectangular window. But as we move smoother windows to that the point to be noted is that these windows have the main lobe width and side lobe width behaviors. So this for those windows it is plotted here, that what are the, you can have this is a rectangular, and the Hamming window, Blackman, and Bartlett window. So see this ripples getting reduced in the sinc function as well. But when we see that in the frequency response, when we see take this separate one, so you can have this is the rectangular window which has 13.3 exactly that here radiant frequency and a 20 log of this is the dB. With respect to the first side lobe, it is 13.3, and you can see the width of this is the main lobe width, whereas the triangular, the width is increasing, and this is going to be 26.5 here, 26.5 compared to this level. Bartlett, and then the Hanning window, which is minus, this level is here further minus 31.5, and the width is further increased, and you can see the good roll-off rate also. Hamming doesn't have this good roll-off rate, but it has this window here which is having 42.7. okay, so still that width is different from the rectangular window, which is more. And the case of Blackman window, which is having good roll-off rate, also the minus 58.1 here. So this is 58.1, so good suppression here in the ripples, and but the width is more, just more than these 12 pi cases of them, which is going to be more. So the main lobe width increase. So what is the problem with this main lobe width and the side lobe width? If it is, we need to know the characteristics as we taper. This width will increase, and the suppression is good. This leakage will be good. The roll-off rate is also good. And how can we use these characteristics in the how these characteristics will be affecting the design of the FAR filter? Okay, so let's look at the design in FAR filter design, how we will be using that window functions in the window method. So in the time domain, and this is related to the time domain, and this column is related to the frequency domain, where we have this first desired filter coefficients HD of n. So HD of n, which is in time domain, it is going to be a sinc function of infinite duration. Here this is the desired one. So the desired frequency response HD of j omega is the rectangular function. So this is a rectangular function which is ideal rectangular function, so which is just not possible to realize because of the infinite filter coefficients in the time domain. Okay, so and considering this is the desired frequency response of the filter, and suppose we'll take the low pass filter and the corresponding filter coefficients, and the window function, we choose a window function which may be a rectangular window, okay, and get the frequency response of the window function as well. Okay, so in that case, if we do this, if we truncate these coefficients, the sinc function coefficients, that is in the desired filter coefficients, to using a window function, maybe a rectangular window or any of the useful windows, that is used to Hanning, Hamming, Blackman, or a triangular window, then you will get the truncated coefficients. So these truncated coefficients, that will be a truncated sinc function. So you have the finite durations, the coefficients. So those functions are nothing but the coefficients desired for the filter. Okay, h of n, h of 0, 1, 2, 3, 4, 5. So that, and if you look at the same thing in the frequency domain, which is the desired frequency response of the one filter we have, filter coefficients in this case, and the second one is the window function and its frequency response. If we convolve this two, if we convolve them, then we get the frequency response in the here the design h of j omega. So by picturizing that, if we have this h of n, suppose we have the, I just put it in there. So infinite duration 1 of this is HD of n, so which has these coefficients, for example. Here is this is the coefficient of n. Okay, so in the time domain, there's consider this is infinite, it is here, and what would be the Wn? and here we have supposing choosing this window function as number of coefficients and then becomes 0. Suppose a rectangular window. Okay, these are the window function. This is a window function, and if we multiply this 2, okay, so what we get here in the time domain, so for this width, so you'll have the same function up to this point. We'll have this up to this point, that is h of n, the filter coefficients. This is n over here. So this is the time domain. So that is multiplying the two of them, depends on the magnitude, and where it after this becomes 0, this 2 will be 0. So in frequency domain, if you consider this equivalent, the frequency domain hd of n, and it's equivalent to in the Fourier domain, which is omega hd of e power j omega or h of omega. For simplification we can do it. So this is going to be a function which is having the rectangular, the low pass filter. Okay, so this is the cutoff frequency. We can have this omega c, and this response in this window function will have the frequency response as in the frequency domain equivalent w of e power j omega. So the rectangular function would result in here a sinc function. So if you convolve this 2, we'll get h of, this is desired, and here is h of e power j omega. So in which you have this, when we convolve this 2, here is a convolution operation which results in here you have the not perfectly some of the ripples, and then have this filter. So it won't be like a desired one, ideal one. So because of the truncated coefficients, you have the equivalent in the frequency domain. The filter characteristics would be this. So the ripples will be there in the pass band, and this is the pass band anyway, and this is the stop band of the filter, ideal filter. Okay, pass band and stop band. And this pass band will have the ripple, and the stop band will have the ripple. So these allowable ripples in the pass band and stop band will be given in the design. So how much ripple is allowed in the pass band as well as stop band, and what is the cutoff frequency here, cutoff frequency, and what is the pass band frequency, and what is the stop band frequency. This is omega p, omega s, and omega c will be given in the design. So now this main lobe width depends on number of samples here. Okay, and the main lobe width, it is also depending on the function, which is if it is going to be a rectangular function, which is going, and if it is the omega wn is again the other type of window, Hanning and window, the function would be really more, the width will be, main lobe width will be more at side lobe. So main lobe and side lobe width so can be adjusted. So we have to have the ripples less here, okay, and this transition band, which is the important one, depends on the main lobe width. So we'll see that in the next class, how the relation between this main lobe width and the transition band of the filter are proportional. If you have the larger main lobe width, the transition width will be more, and or if it is less, and if it is going to be less. So we should have the transition in the filter design, we should have the transition, the cutoff would be sharper and sharper. It should have this transition width should be, the desirable one is lesser and lesser transition width. But if we want to have this lesser and lesser transition width, then the side lobe will be, in that case this should be minimum, but the windows are giving the main lobe width more and side lobe width reduction is good. So there will be a trade-off between this in the design. So whether you want to have this how much is the transition band, what is the ripples allowed in this case, so that needs to be decided in the trade-off should be taken care in the design process. So we'll see this filter design taking different examples in the how to do this FAR filter design. So what are the coefficients? Finally, we are going to decide these coefficients, which will have the linear phase characteristics as well. So I'm not showing the phase characteristics here, it's only the magnitude characteristics. We would study this magnitude characteristics and the design, and once we get the coefficients, how that coefficients can be used in the Verilog module to design the filter, develop the Verilog module for FAR filter, how these coefficients can be used in the some of the simulators who can design these filters for you. Also, that would also be given in the next lecture. Thank you.